Okay, let's go over homework 3 and move on. So we got 350 grams copper. Okay. So first thing we need to do is make it move fast enough where we can reach its melting point. So if it's where we start this at 22 degrees Celsius and its melting point is 1085. So that's going to be Q equals 350 grams times 0.092 grams per centimeter. Sorry, calories per gram degree C. It's better. And then my change in temp is 1063 degrees C. All right. 50. This one's 0.92 times 1063. So I got 34,229 calories. All right, so we've heated it up to its melting point. Now we're going to melt it. And so Q equals 350 grams, and heat of fusion is just 49 calories per gram. What's significant about it only being 49? It's low, right? It's easier to melt. Once you've gotten the copper to its melting point, it's easier to melt copper than it is to melt ice. All right, and then we're going to take that melted copper up to its boiling point. So that's going to be another 350 grams, 0.092 calories per gram degrees C. And what is this? 2562 minus 1085. So that's 1477 degrees C. All right, so 350 times 0.092 times 1477. So 47559 calories. Okay, so we've taken it from freshly melted copper up to the boiling point of copper. Now we're going to boil it. I'll put the Q up here. So it's still 350 grams. And then the heat of vaporization is 1212 calories per gram. So why is that so much larger? I mean, it was 49 to melt it, and it's 1,212. What was this major difference between melting something and boiling something?
Breaking the bonds.
You're basically loosening the bonds when you melt something. And I say loosen because it frees them up to move about, but they don't disconnect from each other. And when you do the boiling, they fully disconnect from each other. So that full disconnection is energy intensive. So 424200 calories. And then the last one, what are we doing? Just got to take it up another 38 degrees. So degrees 350, 0.092 calories per gram degrees C. And then what is it? It was the 38 degrees C. So 350 times 0.092 times 38. And so this last one is calories. And so then we just add all those together. 3 plus 4200 plus 229 plus 17150 plus 4795. And I got a total value of 524361. We've got two significant figures, so it's Board, sorry, it's 52. I missed a zero there. 36, 2, 3, 4 calories. So 420 calories or 520,000 calories to get that to happen. Is that a lot of energy? I know it's a large number, but is it a lot of energy? Do you remember the definition of a calorie? This is science calorie, not food calorie.
Well, it's thousands of food calories, but it's got to do with water, right? Something.
It's something to do with water. Yeah.
1 gram or 1 degree Celsius.
1 gram of water, 20 or 1 degree Celsius. So that's 20 drops of water. And I'm going to raise that temperature 1 degree Celsius, which is about 2 degrees Fahrenheit change, but still it's only 1 degree Celsius. And so let's forget about this for a second. The calorie that is a science calorie. Let's say that this is a food calorie. So how many food calories are we talking about? A Big Mac. That's a great example. It's about a Big Mac. So if I wanted to take this 350 gram chunk of copper and vaporize it all the way up to 2600 degrees Celsius, you could find that energy in a Big Mac. So it's not a ton of energy. But then the other way to think about that is how much energy is in a Big Mac? A lot. That's depending on your size, between a quarter and a fifth of your total body calorie content that you should have on a day that you're not like super active. Your calorie content for the day should be between 2000 and 2500 if you're not, actively like crushing workouts. So there's a lot of energy in food, right? There's a lot of energy in food. I mean, think about that. You're going to take this 350 grams of copper and vaporize this stuff, literally gas. That's a metal that has been turned into a gas. And that's not even a quarter of your calorie content for the day that you would require just to exist on a regular day. Okay, how about this next one? It's too big. What's going on with this?
An electron is going from the lithium to fluoride.
That is going there, right? That's why it's gone from here and this turns into a 6. So we're just talking about something that has become positive and something that has become negative because the electron from here has gone down there. And our definition for chemistry was study the property of matters and actions of electrons. So an ionic bond formation is that's part of that definition, right? The action the electron has taken is the lithium has transferred the 1 electron it doesn't want to the fluorine that wants 1 electron. What do you think this reaction looks like if you were to take elemental lithium and elemental fluorine and put them in a container together? Does the lithium want to do what it's doing here in this problem? And does the fluorine want to do what it's doing here in the problem? So is this like a mild reaction or violent reaction?
It's violent when they really want to do it.
It's violent when they really want to do it. They really want to do this. I mean, if I just took the lithium and dropped it into a pool of water, it catches the water on fire. Like that's how violently the reaction is because it's desperately trying to get rid of that 1 electron that it doesn't want. This is why you can't find lithium. When somebody says they have lithium, they don't have lithium. What do they have? Lithium ion. It doesn't exist outside of controlled circumstances. I used to have some, but we used it in an experiment. But I mean, I had, I don't know, like 3 pea-sized chunks of it. That was it. And it was something ridiculous, like $80 for it. So you have to use electricity to shove the electron back in, but you also have to do it in an environment that's got no oxygen. So basically you run the reaction in either a nitrogen tank or a noble gas tank like argon or neon. And then you have to glove all that and put it together into a container that is filled with probably mineral oil, because that won't react with it. And then that's what you get. Like I order it and I get this container that's got just looks like a bunch of mineral oil, and inside of it there are a couple of chunks of elemental lithium. So it's not something you can get yourself hands on. Just as a side note with this, since lithium is such a big deal for us right now, what does a lithium mine look like? Do you guys have any idea? What do you know about lithium solubility? Solubility rules, things you were supposed to have memorized. Where is it on the table? Towards the left side? Fully on the left side, right? It's a group 1 metal. Do we know what we're talking about with group 1 metals?
So
Fully soluble. So how do we get it out of the ground? Do we go down and dig it? We don't. So I've seen this dumb image that floats around on Facebook and whatnot of a copper mine. Copper has to be mined because it's not a soluble metal. So you literally just dig those concentric circles. And we've probably seen those things, like the size of a city is what this thing looks like. And it's a meme by guys who evidently for some reason don't like electric cars, and they're trying to say, well, this is bad for the environment because this is how they mine lithium. It's not. This is how you mine lithium. You don't mine it. You drill a hole about this big in the ground, deep, and then you pump water down it. You drill another hole and the water comes flying out. What comes flying out with it? Lithium salts. So you don't have to mine. You literally drill holes and pump water into it. And why does that work? Because lithium's a group 1 metal, so it's soluble. That's it. Super easy. We could pull it out of the ocean. It's just, this is more efficient. So this is for some reason, some portion of when the planet was formed, there was a chunk of lithium here that reacted over time as oxygen became a thing on the planet. And then now I've got all these lithium oxides, but they're fully soluble. So you just get it wet and it comes out, and then you use electricity to pull the lithium away from whatever else is there. So it's the least intrusive mining, although any mining is bad because that's not the only thing that came out of the ground, right? Lithium salts weren't the only thing, other things came out. And so what they do with this wastewater and the muck that's left over is the problem, can be the problem. But, oh, here's the image right here. Found it. No. Open, I get open image in the new. Oh, this thing's in the way. God. Does anybody think that thing that says that cookie thing is important? You guys even know what I'm talking about? Image in the new tab. There we go. Yeah, like nobody reads it. So like, what was the point? This is the image that gets popped up on Facebook that says, is lithium really good for the environment? Because this is how they mine it. It is not in any way how they mine it. It would be phenomenally inefficient to do it like that. It wouldn't even work.
I have a question about the violence of reactions we were
Yeah.
talking about. So like nitrogen in the air into is got the triple bond.
Uh-huh.
So it takes a ton of energy to break that bond.
Uh-huh.
But in terms of when you're saying it's violent, it's not a violent reaction. So it's not a means of how much energy you have to put in. It's how much
you get out.
it wants to.
Yeah. When I say violent reaction, I'm thinking about an exothermic reaction, a reaction that gives off a whole bunch of energy.
Okay.
And if you wanted to think about that the other way, it would take a lot of violence to disassemble the nitrogen bond,
Okay.
because it's that triple bond. And I talked about it in the video that it's lightning bolts and whatnot to get that to separate out. But yeah, when I'm saying that a reaction is violent, that's what, when I put these two things together, what happens? And so a large amount of release of energy would be considered a violent reaction. All right, polar. What do we have for a polar bond? You could go two different ways with answering this. And I saw both on the homeworks that were submitted.
Well, it is a type of covalent bond, but has an uneven distribution of electrons. The electronegativity.
So a covalent bond is sharing of electrons, and this is a covalent bond that has uneven sharing of electrons. That's a perfectly valid answer. The other thing you could say is you could talk about the electronegativity difference. If it's between 0.5 and 1.9, difference between the two things involved in the bond, that bond can be a polar bond. And if it's less than 0.5, it won't have uneven sharing. Okay, so which of these three are polar? Ooh, so the hydrogen's electronegativity is 2,2, the carbon's 2,5,5, the nitrogen is 3, and the oxygen is 3,5. So if we go with that last thing that I said about differences in electronegativity, the carbon-hydrogen bond is nonpolar because the difference is less than a half. The nitrogen and the oxygen, those, if I subtract 2.2 off of each of those, I'm definitely over my 0.5 threshold. So those are definitely polar bonds. Do you guys remember where those electronegativity numbers came from? We talked about that in 121. Condon, does that ring a bell? The guy who came up with the numbers is from Condon. His name was Linus Pauling. The only person to win 2 Nobel Prizes by himself. One for chemistry, and it wasn't even for this. It was for something we're going to talk about today, actually. And the other one was for peace, for getting all the countries that have nuclear weapons to stop blowing them up in the air. Couldn't get him to stop blowing them up, but he got them to blow them up underground. We all have an increased level of exposure to radioactive materials because we blew up bombs, and it's almost exclusively us. By us, I mean the US. Of all the nuclear weapons that were exploded in the atmosphere, we've exploded about 98% of them. It's easily over 1,500 of them, us.
There's a video online that shows like a time lapse. It just has a map of the world. And then it just has a little flash and it goes through the year. And in the 50s.
In the 50s,
It's the whole
Arizona
US,
and
it's just-
New Mexico are just devastated.
Yep.
It is the conspiracy theory as to why John Wayne died. Because he did all those movies in New Mexico and Nevada, and then died of cancer afterwards. And I can't say that that didn't actually happen. That wasn't the reason. Oh, that was it. Okay. Stop that.